Hello, everyone. Today, I'm excited to share our work at the XR Research Center, Sejong University, on making information seeking in virtual reality more intuitive. Searching in VR is often a cumbersome process that breaks immersion, and our research addresses this by asking, which strategy should a user use and when? Unlike desktop search, VR requires us to navigate and locate targets in 3D space. While we have techniques like raycasting or voice commands, their effectiveness depends heavily on the context, like how far an object is or how cluttered the room is. Currently, users have to guess which tool is best, which often leads to frustration and a loss of immersion. Our work builds on established research in immersive information behavior, which shows that searching in 3D is fundamentally different from 2D due to spatial cues. While many specialized techniques exist, from hybrid selection to multimodal voice commands, they are usually studied in isolation. Our research addresses the gap where users are left to manually choose between these tools without any system-level guidance on which is most effective for their specific environment. We first defined a taxonomy of 5 search strategies. This includes familiar methods like direct selection and voice-only queries, but also more specialized techniques for groups of objects and for targets that are distant or hidden. In the select to search method, the user can point to an object using a ray, select it, and ask a question.
Is this plant called daisy?
In the screenshot to search method, the user can capture a screenshot and ask a question about it.
Tell me a little bit about this carpet.
In the voice-only strategy, after exploring and not finding an object, the user can ask a question through voice.
Where is my car key? I can't find it.
In the circle to search method, the user can draw a freehand circle and ask a question about a group of objects.
Which one is the contract document?
And finally, in the world in miniature method, the user can use the whim to select objects that are far away and out of view, and then ask a question.
What's the name of the artist who made this artwork?
Strategy selection isn't random. It's shaped by the situational context. We identified several factors across 3 layers. The task type, whether you're browsing or looking for a specific item. The object properties, like its size and distance, and the environment, specifically how much clutter is surrounding your target. Our framework automates this decision-making. The system analyzes the user's current context in real time, processes it through a predictive model, and proactively recommends the most suitable search strategy. This shifts the choice burden from the user to the system. In our first study, we collected ground truth data from 42 participants to see which strategies they naturally preferred across 32 varied scenarios. We used this data to train a multi-layer perceptron model, which achieved a high accuracy of 94% in predicting the correct strategy for a given context. For our second study, we evaluated the effectiveness of this adaptation against a free search baseline and an LLM-driven approach using Llama 3.2. We wanted to see if system-led guidance actually improved performance and if a generalized LLM could compete with a specialized ML model. ML-based search resulted in the fastest performance, followed by the baseline, while the LLM-based condition was the slowest due to additional processing time required for unstructured outputs. Both ML-based and LLM-based search significantly reduced the number of attempts compared to free search, with no significant difference between the two adaptive methods. Both ML-based and LLM-based search significantly reduced overall workload compared to free search, with notable reductions in mental demand, temporal demand, effort, and frustration. Both ML-based and LLM-based search were rated significantly more usable than free search, with no significant difference between the two adaptive methods. A key takeaway from our study is the trade-off between speed and cognitive ease. While the ML model was the fastest, users rated the slower LLM just as highly because it provided clear reasoning and reduced their mental effort. We also found that object proximity is the primary factor users consider when choosing a tool. Despite these positive results, there are limitations. Our current system is limited to a taxonomy of 5 strategies and doesn't yet provide adaptive feedback, meaning the results are always presented in the same format regardless of the task. Finally, we need to test these adaptive models in more dynamic environments, such as collaborative work. In conclusion, we've shown that shifting the burden of strategy selection to the system creates a more intuitive and user-friendly experience. Moving forward, we aim to integrate intent detection so the system knows exactly when to nudge the user with the right tool. Thank you for your time.